Okay, so today we're going to be proving DeMorgan's laws. First, we're going to go over some notation. So S and T, so this, S, this, T, they are sets. So they're like, sort of like spaces. And this U shape right here means anything in S, anything in T, and anything in S and T. Okay? So a great way to visualize this is, let's say this space right here is S, and this space right here is T. Well, then S, U, I'm just going to call it U for now, this U shape here, SUT would be everything in here, so all these particles in T, all the particles in S and T, and all the particles in S, and would not encapsulate anything outside of ST and S and T. So, this is all of the X that's outside of it. It wouldn't care about that, okay? And so the C here, sort of to the power of C, means everything outside of that. So, well, this is pretty easy. Everything outside of this is, if we put C on this, then it's literally just S, T, and all the particles are outside, because all the particles have been pushed outside. And this is going to equal the intersection. So this N thing is the intersection of what's outside of S and what's outside of T. So let's do that then. So first let's do what's outside of S. So it's going to be, well, let's draw S and T, because this might be easier. So what's outside of S? I'm going to draw the box as well. I'm going to do the whole, we're going to do the whole thing here. What's outside of S? Okay? Well, T's outside of S. So technically all the dots would be around T. But it's the intersection, which means it's what's outside of S and T, right? I think it's better explained if we do this first. So you have S, that N shape, and then T. So this just means, I'm going to draw this box right here, okay? So you have S, you have T, and this N means anything that is shared by S and T, okay? It's only their intersection. So this case, it would only be this, because that is the shared space. So in this case, the one up here, we're looking for the shared, when S and T sort of release their particles, or whatever you want to call it, and sort of make it so that it's away or out of S and T. Where is it out of S and T? Okay? And that again is literally just this. It's wherever it's outside of S and T. The intersection. Right? So this is the intersection of outness, if you will. I don't know how much sense that makes, but it makes sense in my head. Okay? So here's the last one. We're gonna do the last one here. So we get rid of this. This proof is super important, at least I believe, to do visually. I had a lot of fun doing this, writing it all down rather than thinking about it, because it's not like impossible to picture it, but I think it's just easier to do it on paper. Anyway, so we have S, N, T, which again is the intersection, but it's everything that's out of that. So you need to just basically reverse the colors, right? Like you gotta, like if blue means in and red means out, in this case red means in, blue means out. You're just it's like opposite day, all right? So we know what this is. It's just the intersection. So C would just be everything that's not there. So you have your S, your T, and that's your intersection. Well, we know that it's just everything that's outside of it. So there's particles in T, there's particles in S, and there's particles all out here. Okay? And so now this one's a fun one. I remember getting confused about it, but it's actually not that hard. Okay. So you have your S, you have your T, you have your X. So, again, we're everything that's outside of S, everything that's outside of T, okay? But this time, we don't just care about the intersection, we care about what's also just not outside of S and what's also just not outside of T. So we now don't care if there are some of S particles, some of T particles. We care about the intersection, and we also care about S's unique outside of and T's unique outside of particles. And the best way for me to show you that is ignore T completely right now, and we're just going to draw dots around S, but not in S. Well, they'll be in T, they'll be around here, they'll be all over here. Okay, ignore S now, just focus on T. Now we're just going to draw a particle just outside of T. Well, there's going to be some in S, there's going to be some out here, there's going to be some out here. Oh, that looks exactly like that. It's the exact same thing. So that's the proof. That's it. I don't think there's any reason to dwell on it anymore. You've just proven DeMorgan's laws by picturing it, by having a little art competition with yourself. And because you're doing linear algebra, you win because no one else wants to do it. Thank you for watching.